This is problem 1213. In this problem, we're taking our understanding of hydrostatic equilibrium that we learned yesterday, and we're applying that to the dense core of a giant molecular cloud. So the first thing it asks us to do is calculate the pressure gradient at the moment of collapse. So that just comes out to the pressure of the cloud over the Jeans length. And it asks us to do that using the ideal gas law. So the ideal gas law is pressure times volume equals N, which is the number of particles, K, the Boltzmann constant, and T. We learned today that N can be substituted in for the total mass over the mean molecular mass times the mass of hydrogen. Volume is just mass over density, so we set those in, move the equation around a bit, and we get this expression for pressure at the cloud using things that we know. The density is given in example 12.2.1, as is the temperature and the mean molecular mass. The Boltzmann constant and mass of hydrogen are in appendix A, and for our Jeans length we compute that in problem 1210, and that equals 5.086 times 10 to the 15th meters. So now that we have our equation and everything except the pressure, we just enter all those values in, and we find the pressure of the cloud over the Jeans length is equal to 2.434 times 10 to the negative 28th newtons over cubic meters. So we know from our understanding of hydrostatic equilibrium that the force of pressure must counteract the force of gravity in a hydrostatic star, and that concept is represented by this expression of the pressure gradient. And so the part B asks us to find the pressure gradient using this expression, where we have the gravitational constant, the mass given in example 12.2.1, is 8 solar masses, which is 1.59 times 10 to the 31 kilograms. Density is the same, and radius is just our Jeans length. So we insert all that into our pressure gradient equation, and we find that the pressure gradient equals 1.23 times 10 to the negative 27th newtons per cubic meter. And so we can see when we do a ratio of our answer from part A to part B, that our answer from part A is significantly lower than our answer from part B. So what this means is that the pressure gradient in this cloud is at the Jeans radius is unable to balance the force of the gravity. So basically the cloud is just collapsing in on itself due to its own force of gravity. Right, so part C of this problem refers us to this equation 10.5, and it asks us when we're trying to basically look at the acceleration of the decreasing radius of the collapsing cloud, why we don't need to really include or worry about this pressure gradient. And so we can just simplify that equation to equation 12.19. And so basically we can compare these two terms as the radius shrinks when the spherical cloud is collapsing. So we take this term, we turn that rho into mass over volume, so we can get it in terms of radius, which ends up with us having r to the 5th in the denominator. So this whole term is proportional to r to the negative 5th. We do the same thing with our pressure gradient using the ideal gas law expression that we found in part A, and there we find that we get r to the 4th in the denominator, so that this pressure gradient is proportional to r to the negative 4th. So then we take that pressure gradient over this expression, and that will be proportional to r to the negative 4th over r to the negative 5th, which is equal to r to the 5th over r to the 4th, which is just equal to r. So basically this whole thing is just proportional to radius r. So when the cloud is collapsing, r is decreasing, and as r approaches 0, this whole term, because of the proportionality, will also approach 0. And from that we know that if this is approaching 0, then the numerator has to be much smaller than the denominator. So therefore, we have this inequality, and we can decide not to include the pressure gradient in this equation.